Hello Physical Science, this is Mr. B, and we're starting Section 2 today, and the title of Section 2 is the gas laws, and the reason why we need to have so many laws are kind of focusing on the gases compared to solids and liquids is that solids and liquids are a little bit easier to predict the behavior of than gases. Again, gases are more spread out. Again, they don't have a definite volume or a definite shape, so their behavior has to be defined by several laws, and again it kind of changes a little bit more compared to a solid and a liquid. So we're going to focus on, again, things that govern how gases behave and talking about different types of pressure and things like that. So our example that we're going to start with, and we'll come back to this here towards the end of the video as well, talks about breathing. And so when you inhale, again you can do this right now, the volume of your chest cavity increases. So you can feel that when you breathe in, you kind of just, your stomach sticks out a little bit, and that's because your chest cavity, the volume is increasing, and then air will come into your lungs. Then when you exhale, like that, you can feel, again, the volume of your chest cavity decreases, and then air is pushed out of your lungs. So changes in the volume, the temperature, the pressure, and the number of particles have predictable effects on the behavior of a gas. And this is really what this video is going to focus on, is how volume, how temperature, and the number of particles, actually it's how they affect the pressure inside a container when we talk about gas. So to start, again, like I said, we're going to mention talking about what causes gas pressure in a closed container. So that's what going to be our focus is. And to start, pressure, I would definitely write down this definition when we talk about it in terms of physical science, is the result of a force distributed over an area. So this will make more sense once we actually get some examples, but it's basically how much, again, how much maybe you're getting pushed against, and again, over how big of an area. So you're feeling something being almost like being fought back against, again, and over whether it's in a large area or over a small area. And again, we will give you some real life examples to kind of help pressure make a little more sense. So right now, I would just make sure I have that it's the result of a force distributed over an area, and collisions between particles of a gas and the walls of the container cause the pressure in a closed container of gas. So the reason why we feel pressure inside closed containers is because there's constant collisions between the side of the container and, again, the number or the particles that are inside there. And we're going to see here in a little bit that there is a large number of gas particles inside closed container at any given time. So here's a real life example that kind of helps illustrate pressure, I think, pretty well. So it talks about a moving hockey puck. So a moving hockey puck will exert pressure on any object it hits. And to kind of go along with this, there is a layer of shatterproof glass that protects spectators. And our example says the faster the puck is traveling, the greater the force of the puck on the glass, which is kind of self-explanatory. So again, if someone hits a puck at 10 miles an hour and hits a glass compared to 100 miles an hour, when it hits the glass at 100 miles an hour, the pressure that it's going to be exerted, again, the force of that moving puck, means that there's going to be more pressure on the glass. So again, the faster you move, the more pressure you feel. And then another thing, which is really important as well, is that the smaller the area of impact is, the greater the pressure. So if the edge of the puck hits the glass, it exerts more pressure than if the face of the puck hits the glass. So this might seem a little backwards. You might think, well, the more space it comes into contact with, the more pressure there is. But a good example could be if you just hold your left hand facing up and you put your entire palm and push down. Again, not too hard, just push down, and you can feel a pressure from your palm pushing down onto your palm. But then if you just take your right hand and you just put your pointer finger and you push with the same amount of pressure, you can feel that more. So the smaller the area of impact is, again, you might think this is a little backwards, it's the greater the pressure is going to be, because you have that same amount of force that's concentrated in a small area. So that is why, again, pressure, again, if you have the smaller area of impact, the greater the force or the greater the pressure is going to be. And that will make more sense because we derive pressure, again, when we talk about our SI units, from force and area. So that means that how we measure pressure is basically taking how much force we have and we divide it by how much area it has taken up. So force is measured in newtons and area is measured in square meters, and this gets a little bit confusing because then we called our SI unit for pressure the Pascal. So it's just a shorthand way for writing newtons per square meter. So this is, again, I would definitely write this down, that we measure, again, remember our SI units are used so we can readily repeat experiments no matter where we're at in the world. So when scientists measure pressure, they use a unit known as the Pascal. And again, it is just dividing how much force something has over how much area it has encountered. So that is what a Pascal is. And scientists will often express larger amounts in kilopascals or kilopascals. So if you remember going back from chapter 1, I know this is a while ago, kilo means 1,000. So 1 kilopascal is equal to 1,000 pascals. So it's a little bit easier, again, to write things out using these prefixes whenever the numbers are a little bit larger or when they're a little bit smaller. So in the case of pressure, that's usually a higher amount, so that is why the kilopascal is used. So that is our SI unit. So that's actually how we measure pressure. And to get an actual example of how gas pressure or pressure works when we talk about gas, we talk about helium atoms in a balloon. So we've all, hopefully, or sometimes in our life, encountered a balloon filled with helium. Again, they're the ones that float in the air. So they're constantly moving when they're inside the balloon, and there are more than 10 to the 22nd helium atoms in a small balloon. And that is just a gigantic number there. So there is a ton of atoms even in a small helium balloon. And so when these particles collide with the walls of the container at the same time, they produce a measurable pressure. So we have all squeezed a helium balloon before. Surely probably a lot of us have popped them. But when you squeeze it, again, you can't just completely cave it in upon itself. Again, it exerts a pressure back onto you. And again, if it's small enough, you might be able to push it in a little bit. But you can feel a little bit of a force pushing back on you. There is some pressure inside of that balloon. And so the reason why there's that pressure is because those 10 to the 22nd atoms are constantly hitting the walls of the balloon. So that's what causes the pressure. So the reason why you can't just smush it up into a little tiny balloon inside your hand is because those helium atoms are fighting back. They're putting pressure. So the more frequent the collisions, the greater the pressure is. And so the speed of the particles in their mass also affect the pressure. So all of those are going to come into effect when we talk about, again, how pressure comes into effect and why we have force in a helium atom or inside of a helium-filled balloon. And again, if you try to squeeze that too hard, the pressure will get so much that the balloon can't take it anymore, and then it pops. So it's not like we can just cave it in upon itself. Eventually, the force will fight back so much that it will be too great for the balloon to withstand, and it will pop. So that is what, again, some real-life examples of how we measure pressure. So now we're going to look at factors that can affect our gas pressure. So there's factors that can make it go up and that can make it go down. Now we're going to focus mainly on what increases gas pressure. So the factors that affect it are temperature, volume, out of order, temperature, volume, and number of particles. So each one of these is going to get their own slide. So I'd make sure you get them jotted down as we go here. So here's how temperature can affect gas pressure. So raising temperature of a gas will increase its pressure if the volume of the gas and the number of particles are constant. So this is important. So if we only change the temperature, so if we increase the temperature from 50 degrees Celsius to 100 degrees Celsius, which again, that's a big temperature change, as long as we keep the volume and number of particles the same, that will cause the pressure of the container to go up. And we're going to actually get another real-life example. So there's a lot of examples here to kind of help us understand this a little bit better. So we talk about over here, there's a firefighter using a pressure gauge to check the air pressure in his tires. And so if he checks the tire pressure again after a long drive on the highway, he will find that the pressure has increased. And the reason why this has happened is from the motion of the tires. So the motion of the tires on the highway heats the tires, and therefore it's going to increase the tire pressure. So what happens is, again, looking at it at the atomic level, the average kinetic energy of the particles in the air increases. So the energy of the motion, again, kinetic energy is energy of motion. So as the temperature rises, there's more kinetic energy. And with this increased kinetic energy, the particles move faster and they collide more often with the inner walls of the tires. And faster moving particles hit the walls with greater force. And we put that all together, there's more collisions and increased force cause the pressure of the air in the tires to rise. So again, basically, we increase the temperature. When that temperature is increased, there's more collisions, and the particles move faster, and they have more force. So increased temperature means an increase in pressure because of all of these things right here. Again, more kinetic energy, more collisions, more pressure. So that is how temperature affects it. And now volume. So volume is just the amount of space that it takes up. So reducing the volume of a gas increases its pressure if the temperature of the gas and the number of particles are constant. So if we make the size of the container smaller, the pressure will increase. So our example right here is a pretty one that we've probably all done. So if you take an empty plastic bottle and twist the cap onto it and then you squeeze it at the bottom, what's going to happen? So if you take it, you squeeze it at the bottom, you crunch down the bottom, so that means the volume of the plastic bottle begins to decrease, and as the volume decreases, the particles of the trapped air collide more often with the walls of the bottle, and the pressure in the bottle increases. So again, all you're doing, you take a bottle, you squeeze it, again, you have less space for the gas particles now, so therefore, with the space that they're confined to, they're colliding more often, they're hitting the side more often, and the pressure in the bottle is going to increase. So that is how volume affects it. Again, decreasing the volume, and we'll just skip over that for now because we already talked about how the diaphragm can be affected, and again, we can maybe go over that a little bit more in class. And our last one is the number of particles. So increasing the number of particles will increase the pressure of a gas if the temperature and the volume are constant. And that's pretty self-explanatory. If we just add more particles into the same size container, there's going to be more collisions, and therefore we're going to have greater pressure. So that is it for the first part of section 2. Let me know if you have any questions.